Thomas Wolf is our very own co-founder and chief science officer at HackingFace, and on top of creating many popular libraries like transformers and datasets, he is also the initiator and senior chair of the largest research collaboration that has ever existed in artificial intelligence, called Big Science. And today he will talk to us about transfer learning and the birth of the transformers library. So, Tom, ready when you are.
Thanks a lot, Sylvain. Okay, hi everyone. Today I'm very happy to make a talk a little bit different than what I do usually. Since you will learn a lot of things in the coming course, right? This is a full week of classes, a full week of chapters to read. So I thought I won't do an educational course like I do usually, but I'll actually talk about the origin of HackingFace and the origin of transformers, the origin of our library, and kind of walk you through a very personal, honestly, selection of what happened in the past few years at HackingFace and in the field of transfer learning. So let's go back in time to the very beginning of why we're here today, at least why I'm here today, which is 4 years ago, 5 years ago now. October 4, Julia, who was an old classmate of me, we were playing music together in a kind of progressive rock band. Kind of talked to me about the coming revolution of deep learning and say, okay, you've been doing a little bit of science at before doing your law degree. Do you want to come back to doing some science? And I was like, yeah, actually, yeah. And so we followed together this Stanford CS224D Deep Learning for NLP class, which was a lot about LSTM, skip thought vectors for those who were already following a little bit. And actually, this is, I think, interesting because today we kind of back to this, right? We're doing a course. At that time, also, we followed that over the internet. There was still no pandemic. It was easier, but still the course was at Stanford. We were both in Europe. And so maybe today, some of you will be following this class with friends, maybe friends in the music group band, or I don't know. And maybe in a few years, we will have a very successful startup that started this week by following this course together. And that's really all that I hope for you. I think for us, it's been an amazing journey from this day to today. And the early days of HackingFace were actually quite different than the HackingFace we know today. We were building an AI chatbot that was a little bit like a talking Tamagotchi. You could like discuss with it. It was the beginning of generative technologies, right? All with LSTM. And you could also send it selfie. There was beginning of image classification to try to understand a little bit what you were sending and to try to reply with something fun. And that's how HackingFace started. We were just 3-4 at this time. But quite quickly, we actually started to open source a little bit of code. So this is a screenshot from the HackingFace GitHub pages 4 years ago. You can see probably libraries and frameworks you don't know because they've changed a lot, but it was the first one. We were really proud of our coreference PyTorch adaptation of an emoji detector, of a like sentimental detector. But why has this all completely changed? Because there was a couple of revolution in the field of NLP a few years after we started, so more precisely around the beginning of 2018, I would say. So I think if you want to date back, this could maybe go back to this first unsupervised sentiment neuron paper from Alec Radford already at OpenAI, where they trained an LSTM on the largest data set that people had at that time, which was data set of Amazon reviews. Well, actually, the internet was already there, but still not a common practice, right, to use that as a training data set. So they trained this LSTM, and what they discovered is that the model, the LSTM, learned to actually categorize sentiment without being explicitly taught to do that. So this was trained in a generative fashion. This LSTM was trained to generate the next token, just like we do today, right? And they also identified, well, something that we don't really use anymore today, I would say, but some specific neurons that were very finely tuned to detect sentiment. And so this was the first hint that unsupervised pre-training with a generative objective could lead to good performances on downstream tasks like sentiment classification. But this was still using LSTM, and the data set was still quite, I would say, domain specific. Amazon reviews are still not, I would say, as widely as covering a wide field of NLP as the data set that we have today. So a bit later, I would say at the end of 2017, so a few months later, were the first, I think, most impactful paper, which was this first ELMO, which is the first this paper called Deep Contextualized Word Representation. That was the ELMO, the beginning of the Muppet names, right, for all these models, which kind of show that if you pre-trained on kind of an LSTM on a wider diversity of text. So this one was unfortunately using a shuffled text. So it only had like full sentence, but not full paragraph. You could actually have good performances on a lot of NLP tasks, and not only sentiment analysis, but also like question answering, textual entailment, and this kind of thing. The idea here was still kind of to extract token representation, more than maybe what we do today with like full pre-trained model. And then really concurrent to this work was the very nice ULM fit from Sebastian Ruder and Jeremy Howard, where they also pre-trained this LSTM, and they also showed that you could adapt it to many, many tasks. So these two papers really at the same time, at the beginning of 2018, people were like, oh, maybe all this approach of transfer learning that we've been using in computer vision and ImageNet for a long time could be useful also in text. And so this kind of led Sebastian to write this interesting piece in around the summer of 2018, which was maybe the ImageNet moment of NLP has arrived, right? And he was very, I think, insightful in saying, oh, pre-trained language model can achieve state-of-the-art results, and that's something that's going to change everything. But this was just one part of the revolution, which is transfer learning, pre-trained model. And the second part was using transformers in place from LSTM. And here again, I think Alec Radford from OpenAI was really pioneering this by using the GPT, the first GPT in 2018. So this was around the summer with this generative pre-trained transformers. And actually, the name really GPT was, I think, only coined in the following BERT paper from Google, which was a few months later in October 8, 2018, where they kind of used this same transformer model, but instead of using it as a causal or autoaggressive model, they used the now famous masked language modeling objective, right? Denoising objective. And so these two papers were very interesting because they mixed this early idea of transfer learning, like having a model pre-trained on a large data set, with the architectural improvement of the transformer, which made mostly the training very efficient, a lot more efficient than LSTM. Though today we have like other, well, maybe we're coming back. I'm not sure. This is maybe what you will be in charge to do if you do research in this field. And what was the conclusion of mixing these two objectives? Well, it was really a storm in the NLP field. So you can see this if you go, for instance, on paper with code. If you check this curve showing the state of the art at various times, what you see is that in around the end of 2017, beginning of 2018, you see this very strong slope upward, right? There was like performance was basically plateauing for like years, right? Here we see that on NER. Since basically 2009, we did not really move up anything. And then from like summer 2018-17, TagLM was already kind of a first transfer learning approach actually. And then with Transformer, we were moving upward very strongly. Squad 2, you see also the same very strong increase in the performance of the model by using BERT. You see the jump BERT single model. There's a very strong jump, 10 points in exact match here metric. And then, well, you can say maybe we're plateauing again today. I think most of the reason we're plateauing is that Squad 2 is now kind of saturated actually as a benchmark. And so we were following that very closely. And basically, when GPT, the first of the names, so this one, went out, we were actually at HackingFace participating in a challenge at NeurIPS. Well, this is an old slide, so we still call it NIPS, but that's now NeurIPS, right? 2018. We were participating in this conversational AI challenge. So the goal was when you have some sort of chatbot, you had to take into account a little persona for your robot, and you have to answer in a convincing way to a user. So it's a little bit like a Turing test, right? But you have a persona. You're supposed to pretend you're this person here. And this challenge was interesting because it came with a nice data set made by the New York Facebook team. And for this first time, GPT was just out, and we were like, okay, maybe let's try this GPT. Let's try this pre-training approach for generative tasks as well. A lot of people were just using this model for classification tasks. And so we tried for the first time to use it for really purely generative tasks like chatbots. And the results you can see on the right were really impressive. We were directly on top of the leaderboard of the competition, and by a very strong margin. The perplexity, the first column, we were like, perplexity is a kind of an exponential matrix. So it's quite hard to divide by 2 the perplexity, but we were like 2 times lower than the other model. Well, this matrix, well, if you've done a little bit of generative NLP, and you will learn that in the course here, it's very hard to evaluate. So this did not translate always in human evaluation, but it was still already very, very, very impressive. And when we studied a little bit and compared to the other teams, what we saw is that if some team were very good on the validation set, they often went very down on the hidden test set. So if you've been doing a little bit of Kaggle, you know that this mostly means that you're starting to overfit on the validation, the public data set. And some team were a bit lower and staying lower, right? Which is more like a sign of kind of underfitting, if you want. And what we saw is that our approach was both using transfer learning and transformer as well, but transfer learning, I think, is the strongest ingredient. Using transfer learning, we were both very strong on validation sets, and we stayed very robust on the test set. Hoopla. And so this led us in the next summer, in June 2019, to do a very long tutorial around transfer learning in NLP with a few friends, Sebastian Ruder, Matthew Peters, who basically created this field, Swaba, who also actually did really great stuff I won't show here, but you should check them out. And what we saw there, well, what we tried to do there is try to explain a little bit what was the idea. And so just as an insight, you will learn more in the course, but basically this is the secret ingredient of transfer learning, is that in traditional machine learning, we had all these separate tasks. This is on the left. You had task 1, you wanted to do NER, you had a data set for NER, and you basically randomly initialize your model and train it from scratch on this data set. If you are now trying to do summarization or chatbot, you will gather another data set of summarization or chatbot, and you will, again, just create a machine learning system specialized for this task. And if you add another task, again, same thing. You will have very separate pipelines and very separate systems who are already, each time trained from scratch. And the approach of transfer learning was to do a little bit more like, I would say, humans do, which is that we don't randomly initialize our brain each time we tackle a new task, right? What we do is that we use all the knowledge that we've learned in the class, in our life experiences, to bootstrap our learning, right? And so when we have a new task, we just reuse all this knowledge that we have. And this gives us mostly 2 main advantages that we see also when we reproduce that with machine learning models, which is first that we are very data efficient, because we can fill the gaps between all the examples that people are giving of a new task. And so we are very data efficient, and we usually reach better performances. And this is also related because we can fill the gap between the data examples that we have on the new target task. We can reach better performances. And transfer learning is a way to try to do the same for machine learning. So to try to build this kind of generic knowledge that can be reused on many, many tasks.
So we have questions that could go here, Tom. Is there a systematic way to estimate how many annotated samples to fine-tune an existing model, for instance, on an R task?
Yeah, that's a good question. It's quite dependent. So really, the direction the field is trying to go is toward what we call few shots. So using less and less examples. So I mean, requiring less and less examples. So for some tasks that you will see in the course, you can actually do zero shot, like text classification. You actually, in many cases, don't need any example. But then it's always very dependent on how specific your domain is. And typically, the more specific your domain is, the more you will need example. And in some case, you might still be outside of the pre-training domain of the model, and then you will need quite a large data set. Yeah.
Thanks.
And so, yeah, let's go. Yeah. Why would this work in NLP? Well, you probably have the intuition, but here they are. The idea is that many NLP tasks, if you take a step back, they share a common knowledge about language. They share that, oops, let's put that back in full screen. Yeah. Basically, if you know, for instance, adjectives, if you know linguistics, then it will help you a lot. For instance, if you want to do NER, right? You want to identify, I don't know, the name of organization. If your model already have a good knowledge about linguistics and know what is a noun, that will help it a lot, because it will know that name of organization are very likely nouns. Okay, they are not adjectives, they are not verbs. So all these things can be useful for the model. The same, right? If your task is in English, if your model know a little bit about English, you can just learn basically the missing pieces that it has on your task, and won't need, I would say, like half of your training data set just to learn how English works in general, right? So tasks can also inform each other. Typically, as I told you, syntax and semantics, they are often related. If something is a noun, that's also mean that it has a meaning related to a noun. If it's an adjective, that's here to kind of change the meaning of a noun. So all the thing. Obviously, annotated data, that is rare. It's very difficult. So the more we can gather it, the more we can gather several data sets together to build a bigger one, the better it is for our model. We know that these neural network models, they are still data hungry, right? We don't have a lot of feature. That's the nice thing about them. But the counterpart is that they are data hungry, because they will need to learn this feature themselves. And now the most, I would say, a down on earth reason why it works is that when we try, it works. So that's currently the state of the art for many NLP tasks. It's to use this transfer learning. So that's also a good reason to think that, well, maybe it has reason to work. So I talk a lot about science here, like transfer learning revolution is a scientific revolution in the field. But if you're here today, it's also because you've probably been following our open source work. And this was kind of started in parallel to that. We always thought that open source and open science were going hand in hand. And so very early, we started to open source some models. So the first one we did is here. It's now the summer of 2018. So just before basically this transfer learning revolution really began. And so we did this neural coherence, which was a coherence model for SPACY, which already show very interesting performances for also a pre-trained actually neural network, but only for coherence. And then there was obviously this GPT. So I told you we were using the first version of GPT in this first competition, and that's where basically we understood that, wow, this was very powerful. And before using it, as always, we actually released an open source version. So actually a bit later, we discovered that some other competitor also used our open source GPT in the same competition. So it was very, very interesting. We actually made a paper together at ACL a year later. So it's a bit the open source way of HackingFace, always trying to do something collaboratively with everyone. I think that we can just get the sum of every open source thing is larger than having just everything private models. And these two early efforts and the interest we saw from people led us to try to do that again. And this led us to the first stone of transformers, which was this conversion of BERT in PyTorch. So in October, there was this BERT model from Google, and people are like, wow, this is really an impressive model. And so when the code was open source in TensorFlow 1 at that time, we thought, oh, that's a little bit a shame because TensorFlow 1 is still a little bit difficult to use, right? And there was PyTorch already at that time. It was PyTorch version 0.3, but it was still quite interesting and easy to use. And so we decided, okay, let's convert this TensorFlow model in PyTorch, and let's see if people will be able to use it easier, right? And our idea here was basically that, well, first at that time, BERT sounded like a very large model. It was 300 million parameters, which today sounds like maybe the smallest model that you use, at least in the research field. But at that time, it was like really, really large. And so we were like, nobody will be able to train that. So we should make it easy to use the pre-trained weights that Google really nicely released. And to make it the easiest, we should actually have them also in PyTorch. And so that's what we did. And that led to this first version called a PyTorch pre-trained BERT. And this was really very far from transformers. But we had a few initial ideas that evolved. So one initial idea was that we could also host the pre-trained weights on our S3 buckets so that people didn't have to go through the painful process of downloading and converting them, and we could maybe just load them. And here we were inspired by Joel Grus's nicely made from pre-trained method in Allen NLP, which I found very, very nice. With just one line of Python, you could download a pre-trained model in Allen NLP. And so I was like, okay, let's actually use the same idea. And so this was the first thing. And this evolved over the coming 2 years, I would say, from 2018 to 2020 to a fully fledged Git version model hub that you will see today, which both, I think, give you very wide access to the model. It's very easy to inspect it, and at the same time give you a lot of interesting like widget to play with the model, online API to use it very easily. So all this you will see in the class, but that's very interesting. And the first idea was also just to give access to BERT, right? But then I was like, okay, we actually have an open source code for GPT, another for BERT. Why not actually make them in a single library? And this led us very quickly to basically a single API, which today I think wrap not far from 100 different architectures, which is the today transformers. And so the first version was PyTorch transformers with 4 architectures. And quickly we thought, now TensorFlow 1 is a little bit hard to use, but TensorFlow 2 is quite nicely done actually. And so we were like, maybe we could have both PyTorch and TensorFlow 2 in the same framework. And maybe we could even make it this so if you want to use TPU to train your model on TPU because you have like free access, you should. And then if you want to fine tune the same model in PyTorch, you should be able to switch very easily from one to the other. And so we tried to make these two main framework at that time, and then later JAX and Flax, which are more recent, in the same framework. And we saw that it was actually not so difficult to get them all together. And to get what is now transformers, right? Not anymore PyTorch transformer. While PyTorch is still, I think, maybe the better supported one, but TensorFlow and JAX are very, very strongly improving. And so this was a transformer. And what we witness is this basically explosion in the number of architecture on model. Most of them are today in transformers because it's very easy to add new one. And so you can see from BERT, there were a lot of following work trying to experiment with variants in the architecture. I think maybe XLNet is a good example where they try to do both some autoregressive but also bidirectional way to do a forward pass in the neural network. And one question became, what is important for all this model? I mean, how do they compare, right? How do you select the model? Which one do you know you want to use? And here, I think what became also quite clear in the subsequent year was that actually more than architecture, it was actually the data that mattered a lot. So I talk about XLNet, which was very interesting as a different architecture and actually got a lot better performances than BERT at the time. And people were like, wow, we should experiment with various architectures for modifying the transformers. And this subsequent work from Facebook called Roberta actually show that it's not so much the architecture, but just the data. XNet was actually trained on a lot more data than BERT, and that's actually what mattered more than the architecture. And so Roberta took very basic transformers, just exactly the same as BERT, and then just trained it on more data. And they got state-of-the-art results. And this was then shown in these two other graphs, which are from the neural scaling paper. And they show that basically the architecture was, the performance were really weakly sensitive to the architecture. So you see at the top, you see this very flat curve for feed-forward ratio, this very flat curve for aspect ratio. And these are all logarithmic curves. So they actually span very large aspect ratio. And basically, as long as you stay not too far from the middle, you're pretty good. The architecture just don't really matter that much. And the T5 paper, who came out later, also confirmed this. Basically, the early transformer paper were already very close to the optimal architecture. But what's very important is this graph on the lower left, where you see the dataset size. This is also from the neural scaling paper from OpenAI. And you see that just by increasing the dataset size, you have this very predictable increase in performances. So here, this is the test loss. So lower is better. And this actually brought us to this question, well, actually, more than architecture, what is important here is data. And so a year later, 2020, actually, or maybe 2019, we decided to do a new library around data. We are like, okay, we also need to focus on data now. And so this new library was called Datasets. Well, early name was NLP, but for a long time now, the name is Dataset. And this library also got some quite strong interests from the community. It passed the 10K stars. Well, I don't know how GitHub stars are relevant as a measure of interest, but it's also widely used by a lot of other work. So I think it's very nice. And this library, the idea was access to data is also very difficult today in NLP, mostly because the situation is very fragmented. If you want to use a data set, you typically need to find where is the code somewhere on GitHub. You need also to pre-process it, and you actually spend a lot of time doing the same work to pre-process the data set. A lot of people are just writing their CSV or JSON loader, so maybe we could share this work and avoid this and just jump to the data structure. That was one note. Another one was that also with this very large language model, we're using now terabytes of data. And this can be very difficult to handle at least on your personal laptop, right? If you want to train a model on 1 terabyte of data like Roberta, this is really a pain because you typically can't load that in RAM. You need to find a smart way to do like just loading the current batch or prefetching. And so we thought maybe we should solve all these issues at the same time. And the idea was that dataset could be a way to kind of centralize access to NLP dataset at the beginning. Now it's expanded to speech and images, but at the beginning it was really about NLP dataset. And also to cover more languages, right? NLP, English, is really the dominant language in research. But in production today, it's not dominant language, right? We have a lot of other, it's still the dominant language, but we have a lot of other languages that are very important. And every time you're actually an NLP person working in another country than the US or UK, basically or India, you want to work with other languages. And so this led us to developing dataset around this effort. So at the end of November, 1 year ago now, November 2020, we did a first community event where we said to the community, we're 15 people at HackingFace trying to add dataset. If you want, you can join. This is going to be fun. We're going to do this together. You will be on our Slack. We'll talk a little bit. And also we'll do some swag and everything. And this was hugely popular. Actually, we had, I think, about 300 people joining to help us. We were definitely a little bit overwhelmed by the success of this fair community effort. But it was very nice also in terms of adding dataset in many, many languages. And the idea is that all these datasets were then very easy to access. And this could foster more research on multilinguality, I think. And so this led us also to write a paper with the whole team. And also there are also some community members actually in this paper. You see Gunjan, Bavitva, they are both like community contributor. And to submit it this year to NLP, where I just actually won the best demonstration paper. So I think this is very typical Hugging Face thing, where we do something very open source. We do that with the community. At least we invite everyone to join if they want to participate. And then we also do that as a science effort. And this all just go together to make something very impactful. And so there is today also this hub that you will see in the course, where today we have about, well, not so far from 2,000 data sets openly accessible. You can even explore them on the hub. And so this was the 2020 effort around data. And what happened in 2021? That was open science more and big science. Well, what happened, I would say it's very personal walkthrough. So I would mean what I actually spent a lot of my time on was this big science effort. And here the idea was that maybe it's time to do very large collaboration in research in NLP. And the example, well, I'm a physics PhD formerly. And so in physics, when we have like very expensive things, we actually gather as a lot of like research lab and try to build them together. And one good example is the Large Hadron Collider, which is in Europe, which is a very, very large particle physics research tool. It costs, I think, 10 billion to build. And it has involved really a huge research community. And it has led to a lot of research work, like you have about 3,000 papers. This led to the discovery of many hadron, and things like that. And so the idea was maybe it's time to do that in AI and NLP. And so maybe why? I mean, why would it be tight to do something like that? Well, again, I think because there was some, if you follow what I've been saying up to now, right, there's this idea that larger and larger data sets are something interesting, some direction we want to go. This was proved again by the GPT-3 paper that show that if you scale again the number of tokens, here you see it in green on the corpus side, and this is again a logarithmic scale. So the scaling is really like, how much is it? 6 order of magnitude? No, 2 order of magnitude bigger than GPT-2. Well, if you scale both the corpus size and the parameter size, you see like very interesting new effects. And these effects are few shots. So recently, I mean, just at the beginning of the talk, somebody asked how many examples would you need? And here in this few shot example, you can see that we just need like 10 examples to get very strong performances. So I don't remember exactly what this curve was in terms of accuracy. Maybe I think it was a classification task. But this one is just extracted from the GPT-3 paper, so you can find it back. And they have a lot of curves similar to this. They have a lot of curves similar to this. And so there was this idea, if you scale this a lot, you get some interesting new effects. And then quickly, what you saw is that there were a lot of announcements of reproduction. Naver Labs trained a GPT-3-like model for Korean. Anthropic, a startup of the Bay Area, raised a lot of money to train similar model. AI21 also trained a massive model called, I think, Jurassic. And another company called Cohere also raised a lot of money to train all this model. And Eluter was also this grassroots collective who trying to reproduce. So a lot of people were trying to reproducing this. But for a diversity of reasons, we were not super convinced about this, mostly because like all these private company did not seems to be targeting like open source release. And Eluter was the only one. But there were still some main problems. So here is a few issues I see. Well, first, all these models, they are not designed as research tool. They're really designed by a company to be like private thing that they want to use for their private product, but they are not designed as research thing. So it's very difficult for academic researcher to be involved in the development of these models, right? And typically when you look at the teams who build them, they're like, yeah, they're like smaller than they should be, in my opinion, mostly because they just belong to one company, and mostly. There is, as again, a lot of environmental cost to training all this model in parallel. If they were open source, we wouldn't need to retrain them like in 60 company. We could just share one, and that would be a nice model for doing all our experiments. And there were some ethical and social issues, mostly since the very beginning of GPT. There's been a stream of paper investigating, okay, how are these very large test corpora? And we saw that they were lacking something. For instance, they were lacking representativeness of some population. They also typically have some stereotypes. So basically, it's very hard to investigate this training data set also because they are typically not open sourced. And so this called, in my opinion, for like a more open and collaborative way to develop this. And this is actually possible because if you look in public, you see that there are supercomputers that are very powerful and that are actually almost fully accessible. I mean, you just need to submit like a grant, an application to say, I need some compute times on this. And they have like almost 2,700 V100 GPUs. So that's quite a lot of compute power. You can train a very large language model on that. So early this year, I started to talk with the operator and builder of Janzé, which is one supercomputer located in France that we knew a little bit from earlier. And they say, yeah, I mean, come train your model basically on a supercomputer. We're very happy. So we kind of discussed a little bit internally, and then we decided that we should actually invite everyone to come join and to train this model with us, and in particular invite the academic community, which was typically outside of all these model creations. And so we filed a grant application for enough compute time to train a very large language model. And this was the beginning of Big Science. Big Science has been going on for like 6 months, a little bit more now, 9 months. And it has already produced very interesting papers. So if you've been following HackingFace account, you probably saw the T0 paper, which involved actually 40 authors. So some of them are from HackingFace, but a lot of them are not from HackingFace. Some are from many universities. And so this type of papers, I think, is very interesting because it's outside of the box. So it's fully open, it's fully collaborative, and it's also show that you can outperform typically GPT-3 on the zero-shot benchmark with a model which is 16 times smaller. So now what we are trying to do is to actually increase the size to 16 times larger. So that's what will begin roughly next January, and to train this very large model on Janzé to see how far we can go, right? With the same idea of like openness, open sharing, and collaborative effort. And so what's next for 2022 at HackingFace? Well, there is obviously education. If we want to have a beneficial impact, we think that this is the way to start. When we talk about bias in data set, when we thought about understanding your model, knowing what is important for your model, basically, we think that we should share all the knowledge we have. There is this strong community. You're all here today. I'm very happy about that too, because you've basically been following more or less what we've been doing. Open source, this is our DNA, and open science, they go hand in hand for me. Sharing knowledge. We try to keep fighting for beneficial, responsible AI. I talk a little bit about data set. This is very important, I think, to understand the bias, to understand the bias of your model as well. And basically try to make this, an inclusive place, right? And while doing all that, doing also this exciting research, when I say we scale this new model to very large sizes, we also try to have some fun and not taking us too seriously, which I think is also a specificity of HackingFace, and why maybe we have this HackingFace emoji, I would say, as the name of the company. So welcome to this course. I'm very happy, very excited about this second chapter. I think it's very interesting. You will learn a lot. And thank you for being here today.
Thanks a lot, Tom. We have a few questions I've waited for the end because they are very general and not directly related to what you were talking about. One is, you talked about a lot about transformers, but what about using graph neural networks in NLP tasks? Graph structures could capture data with complex structures and relationships, and GNN provides an opportunity to study and model complex data representation for NLP tasks.
Yeah, that's a good question. I mean, in all generality, you could consider transformer as a sort of graph neural network. It's not sparse, though it's fully connected, so maybe it could be more efficient. But if you look at like a transformer with sparse attention, in my opinion, it's really close to some graph neural network. In particular, if you use weight sharing like universal transformers. I think in NLP, transformer are kind of dominant today. But yeah, as I told you, in my opinion, the main aspect of the revolution is about transfer learning, more than the specific architecture. So if tomorrow there is a more efficient architecture than transformer, then I would be happy to follow the work there and basically switch to that. Yeah. But yeah.
Another question we had was more about the Hugging Face ecosystem. Is Hugging Face currently becoming commercial from open source? There are many parts of API that are now paid, model training, for instance, with the 2 NLP. Please help me understand the portion of open source versus paid.
Oh, yeah. Yeah, so it's still, I mean, the idea of Hugging Face is, I think, somehow a very typical like open core model. So everything is open source, but you need to do the training yourself. You need to do the training loop yourself. So we do provide examples. That's actually Silva has been doing a lot of work on the examples to have like an efficient training. So you have open source code to train this. And then we also provide some paid solutions, which are mostly there, I would say, to facilitate your work. So typically, if you're in a company, you don't want to wait, you don't have time to actually explore everything yourself, you want some help, then we also here to help. And then we have some specific solution around making this model very fast. And these are typically mostly interesting to companies more than researchers, because they try to lower the latency strongly. And then here, these are also paid product, because people who are interested in them are typically companies who can pay for them. So the idea is that if you're new to the field, if you're a hobbyist, if you're a researcher, you can use all of this for free. And then if you have some like specific needs, like you need to go very fast to put that in production, you need to have like very low latency because you have huge bandwidth in production, then we also here to help, but then we help with our like additional services.
That makes sense. Another question, you hinted a little bit about that at the end, but more fun question is, how did the name Hugging Face and the use come about?
Yeah, this came from our very early inception as a game company, right? We were doing this kind of talking chatbot. It was mainly for millennials, for kids or young adults. So we wanted a fun name. We also thought it would be fun if at some point we became a very big company. I don't know if we'll do that one day, but if we like IPO and then we have an emoji instead of like this very serious name that everybody has, we thought, yeah, let's give this emoji. And I think now it's part of the fun. We like a lot of people are taking themselves sometimes a bit too seriously, I think, in the AI world. So we're here to say, yeah, this is important, but having fun is also important.
Mm-hmm. And a last fun question that people were interested in is more personal. What do you use to build trained models? Notebooks, VS Code, Vim, other?
Yeah, I typically use VS Code. Notebook, I'm always lost in the order of the cells, but maybe I have a bad workflow. Now, I typically use Notebook to explore data. I think it's very nicely done for that. That's the best way to explore data. And then when I train, I typically want something which is very reproducible. So I switch to something where I can git version cleanly and more like typical VS Code. Yeah.
Nice. Thanks a lot for your talk. It was very, very interesting.